Okay, so here I'm starting out the problem with applying that differentiation in the time domain property. So the formula was the Laplace transform of a second derivative was s squared times the Laplace transform of the original minus s times the original evaluated at 0. And then remember, the power of s goes down by 1, the derivatives go up by 1. So s squared, s to the first, no s in the last term. And then the Laplace is like an antiderivative. The derivative of an antiderivative is the original. And then take a derivative again, so you get f prime of 0. So why would we need to use this property when it's so much easier to do it without? Well, sometimes we'll be taking the derivative of an unknown function. So maybe we're trying to find the current, and then, but if it's what, across, I can't remember right off the top of my head. Inductor or capacitor, it's like, you have a di dt or something, and maybe you don't know what I of t is. So there will be times when we have to apply this property. We won't know what the function f is. Okay, so here we can get practice doing it with a function that we know and see that it works out to be the same. Okay, well, s squared times the Laplace transform of the original, and we did that earlier. So it was this, 1/2 1 over s plus 2 plus 1 over s plus 8. Minus s times the original function evaluated at 0. And so I'm just gonna, here's our original function, and if I plug in 0, I have 1/2, and then plugging 0 in for t into the exponential functions, e to the 0 is just 1. So I'd have 1 plus 1, or 2, and then the unit step function at 0, that's when it turns on and is 1. Minus f prime evaluated at 0. Well, here's f prime, and so I just want to plug in t equals 0, so that 1/2 stays out in front, and then I'd have -2 e to the 0 is 1 minus 8 e to the 0 is 1, so -2 minus 8 would be -10. And then the unit step function is just 1. Okay, so I want to simplify this. Hopefully we can get it to look like what we did when we didn't use the property. Okay, so I think what I would do is get a common denominator, in the parentheses there. So I'll leave this s squared here. So that 2 is just out in front, and then the s plus 2 times s plus 8. Okay, so what's the numerator going to be? So this one needs to be multiplied by s plus 8, and the second numerator needs to be multiplied by s plus 2. And then 1/2 times 2 is just 1, so I'd have minus s, and then minus 1/2 times -10, so that's going to be plus 5. Okay. So I'm just going to make, this one big fraction. So I'd have 2s plus 10. I am going to get everything over the common denominator. Actually, this is, this part is just algebra. I mean, so I'd have minus s, and then I'd have to, right now it's just s over 1 and 5 over 1. So actually, maybe I would just write this as negative s plus 5 times that entire denominator. And then I'm just going to show you what we would get and that it's the same. So let's see, I have Maple open here. Okay, so here's what we had actually if you ignore this and this, we had the first fraction minus s plus 5. So I'm going to see if Maple will, I'm just trying the simplify command to see if it will give it to me as one fraction. Okay, this is what we get. It's combining it. This is the answer we got with the first method. And so I'm just going to try the simplify command on that as well. And hopefully it's the same. Yep. So look, it's the same whether we did it using the differentiation property or without. This particular problem, it was much easier doing it without applying that property, but we get the same answer either way. Okay, so it eventually does simplify to that. Okay, 1429 is the one that's assigned. I'm going to do problem 1430, but first just a very brief review of partial fractions. So 1429, it's really easy when your denominator is already factored for you completely, and in 29 and 30, they're factored completely. So when I teach Calc 2, I tell my class, you have as many fractions in the partial fraction decomposition as you have factors in the denominator. So 29, you see 3 factors. So you're going to have an a over the first plus b over the second plus c over the third. 1430, you see, oh, there's an s plus 3 and an s plus 6, but the s plus 3 is squared. So really, you also have 3 factors in that denominator. So there are going to be 3 factors in your partial fraction decomposition. And so let's see, go back to green. The s plus 6 is only there once, so that one's easy. I'll call that numerator C. When you have repeated factors, you build up to the highest power. So the first fraction starts with s plus 3, and then the second, or the denominator is s plus 3, and the second is s plus 3 squared. I guess I don't really need parentheses on just the s plus 3. So the first one is just a over s plus 3. The second one is just b over s plus 3. You don't need like a bs plus c. The only time your numerator needs an s in it is if the denominator has a factor that's quadratic that can't be factored anymore. So like if you had s squared plus 3s plus 1, you can't factor that. So if this was one of the factors in the denominator, then you'd need an as plus b. So your numerator, the degree of the numerator is 1 less than the irreducible factor in the denominator. So here, the factor is s plus 3, that's degree 1. So 1 less is degree 0, or just a constant. And here, even though we have something squared in the denominator, the irreducible part of it is s plus 3, which is degree 1. So another really important thing, and this comes from just college algebra, every single polynomial can be factored into linear and quadratic factors over the real number system. So you should never have an like s cubed plus 8s plus 9s plus 1 or something. You should never have any factor with a degree higher than 2. So everything, once you have it factored, should either be degree 2 or degree 1. And if you just very briefly think about why that is, so think of if you have a degree 3 polynomial, it can either look kind of like that or maybe like this. It's always, there's no way you can avoid crossing the x-axis if it goes up forever and down forever. So, and remember, every x-intercept means, so if it crosses the x-axis, say that's at a, then x minus a is a factor, right? And so you have to have at least one. Like this one may be, there's the x-axis, so it only crosses at one spot. Then the other two roots are complex numbers. So anyway, everything in your denominator should either be degree 1 or degree 2. So your numerators will either only be constants or linear polynomials like bs plus c, as plus b, or whatever. So that's just a little brief review for partial fractions. And then I think the next problem I have us do is where we do have some quadratics that can't be factored. So I'll talk about that next. Okay, the book talks about this method of residues. You can read and learn that, but I just figure, I think Calc 2 is a prereq, so everybody here has already done partial fractions. So I'm just going to use partial fractions and not worry about residues. The method that I teach is I just think about this part and multiply both sides by the least common denominator. So the least common denominator is the denominator on the left-hand side. So if I multiply by this, I'm just left with 2s plus 11 equals a, and then I'd have one factor of s plus 3 left, and then an s plus 6. For the b, both of the s plus 3s would cancel, and I'm left with s plus 6. And then plus c, the s plus 6 is gone, so I have the s plus 3 squared. And you can plug in any values of s that you'd like. It's nice to pick in things that make some of the factors 0. So for me, the first thing I would do is plug in s equals -3. Now, just a little technicality. Technically, this whole fraction here is undefined at s equals -3, but it is defined at s equals -2.999999. So it's sort of like taking the limit. And so I'm just going to plug in the numbers that make that denominator equal to 0. So if I plug in s equals -3, I get -6 plus 11, so that's 5. The a is being multiplied by 0, so it's gone. The b is being multiplied by -3 plus 6, or 3. So I get 3b. And the c is being multiplied by 0, so that's gone. So I get b equals 5/3. Okay, and then I would plug in s equals -6. So -12 plus 11 is -1. And then the a is being multiplied by 0, the b is being multiplied by 0, so the only thing left is the c. And -6 plus 3 is -3, but then I square it, so I get 9. So c is -1/9. And then we still have to find a. You can plug in any number you want. 0, it tends to be nice. So I'd get 11 equals A times 3 times 6, so 18A, plus B times 6, plus C times 9. But we already know B and C, so we can plug those values in. And I get 11 equals 18A. And then 6 times 5/3, well, 3 goes into 6 2 times 5 is 10, so plus 10. And then C is negative 1/9, so 9 times negative 1/9 is negative 1. So this is 9, and then I would subtract 9 from both sides, so I'd get 18A equals 2, so A is also 1, well, A is positive 1/9. Okay, so now I'm going to just rewrite F using those values. So notice this is the first problem where we're finding the inverse Laplace transform. I think that all of the previous problems we've been finding like the forward Laplace transform. So we're going from the time domain into the S domain. Here we're going back. So we're in the S domain, we're trying to get back to the time domain. So I should have mentioned, this is why we're doing the partial fractions. So when you look at this table of all of the Laplace transforms, so we're in the S domain, look at our denominators. So I have S plus A, S squared. So I have powers of S and powers of S plus A, or denominators that are quadratics in S. Okay, so all of the denominators are basically polynomials in S. But I want them separated, right? This table doesn't show you any polynomials being multiplied together. You can have one polynomial to a power, but you never have S plus A times S plus 3. So you have to decompose it using the partial fraction method. Okay, so F of S, then decomposing it. So I have A, which is 1/9, or positive 1/9 over S plus 3. And then B was 5/3 over S plus 3 squared, and then plus C, which was negative 1/9. And that one was over S plus 6. So the inverse Laplace transform, let's see if I can get rid of this here, takes us back to the time domain. So I'm going to do it term by term. This is where the additivity comes in. So the 1/9, that's a constant that comes out in front. And so I just have 1 over S plus 3. Plus, and then 5/3 is a constant that comes out in front. Inverse Laplace of 1 over S plus 3 squared. And then negative 1/9 is a constant that comes out in front, inverse Laplace of 1 over S plus 6. And then you can get all of these from the table. So that 1/9 stays out in front. And then 1 over S plus 3, so that's e to the negative 3t. I'll show you where that is in the table. So here's S plus A. It goes back to this in the time domain. So e to the negative at, and then unit step function. So I'll just put brackets actually, and then I'll have this u of t at the end of everything. So 1 over s plus 3 went with e to the negative 3t. And then plus 5/3. Okay, now it's s plus 3 squared. So let's go back and look at the table. So now we're using this one. So it's t, you multiply by t. So I have t e to the negative at. So it's almost like the last one, it's just I have a t out in front. So t e to the negative 3t. And then the unit step function is at the end, and then minus 1/9. And then this one would just be e to the negative 6t. Okay, I left a little bit of extra room, but then that's our answer. Okay, so 29 should be similar to this one. Okay, 1433 is assigned, and I'm going to do 1432, which is similar. So neither of these can be factored. 29 is prime, you can't factor it. 5 is prime, you can't factor it. So you can't, partial fractions is not going to help you. So when you have a quadratic factor in the denominator that can't be factored, what you have to do is complete the square in the denominator. So it's going to be s squared plus 2s plus something to complete the square, and then I already have a plus 5, but whatever I add to complete the square, I'm going to have to subtract later. So I'm just adding and subtracting the same number. Okay, half of the middle coefficient is 1, square it, I get 1. So now I can write the denominator as s plus 1 squared plus, and then 5 minus 1 is 4. Now I'm just going to go back to that table for a minute, because that was, we see those in the denominator here. So completing the square part plus a number squared. So we're looking at these two right now because our denominator is of that form. The other thing, so we do have an s in the numerator. The thing is, I don't just want to write 2s plus 5, because if you look at this table, when you have s plus a as part of the denominator completing the square, your numerator, it needs to match that. It also needs to be s plus a. So, sorry, my highlighter is not working there. So I need the expression with s in the numerator to match the expression with s in the denominator. So since the denominator is s plus 1, I need the numerator to be s plus 1. So I'm going to kind of use the same trick I used with the unit step function earlier. So I'm just going to add and subtract 1. Okay. And then I'll just rewrite that quick. So the denominator s plus 1 squared plus, now instead of 4, I'm just going to write it as 2 squared, because that was the form it was in the table, s plus a squared plus omega squared. So this is our omega, and then our a is going to be 1. So think of splitting this up as 2 times s plus 1. So just save this s plus 1 right there so that the s plus a's match. And then combine everything that's left. So 2 times negative 1, so we get negative 2 plus 5. So that gives us 3. And you can check, you can multiply out, combine like terms and see, oh yeah, I get the same as the original. Now what we want to do is split this up into 2 separate fractions. So I'm going to do this as one fraction, and then this as another. Okay. So the inverse Laplace transform of f of s, and again, this is for problem 32, not for 33, is going to be the inverse Laplace transform of the part that I circled in green. So 2 times s plus 1 over s plus 1 squared plus 2 squared, plus the inverse Laplace of the part I circled in pink. 3 over s plus 1 squared plus 2 squared. Okay, the first one is set up perfectly to use the table. I would just use the constant multiple rule and bring the 2 out in front. And this one has s plus a in the numerator, so it goes with the cosine. So e to the negative at cosine omega t. So e to the, and remember a was 1, so e to the negative 1t, or just e to the negative t, cosine omega was 2. I'm going to do brackets because I am also going to need to multiply both pieces by the unit step function, so I'll just factor it out at the end. Now this second one doesn't have an s in the numerator, so when you look at the table, the cosine had an s in the numerator, but the sine just has a constant in the numerator. But that constant needs to be omega. We have a 3. What we want is a 2. So we're just going to use that constant multiple rule. And so first I would think of, okay, well, I'll just put a 2 there, but I can't just multiply by 2, right? So I can multiply by 2 over 2, which is 1. And then what I'm going to do is apply the constant multiple rule and pull this out in front. So then I have 3 halves out in front. And then what's left is this 2 right there in the numerator. So now I have omega over s plus a squared plus omega squared. So now it perfectly fits the sine part in that table. So it still had an e to the negative at, and then it was sine omega t. Okay, and then again, I left a little bit of extra space there, but okay, so this is our answer. Okay, the next one, I'm actually going to do this homework problem for us, problem 39, but it's not short, so I'm going to make a separate video just for that one. Okay, so here it says 1445 is assigned, but 1441 is like it, so I will do, and this is the last one I'm doing in this video. So I'll do 1441. So again, this is going to be a partial fraction decomposition. And notice in both problems, there are 4 factors in the denominator, because in 41, I'll have an s plus 2 cubed and an s plus 3. And you have 2 factors that are squared. So it's the same sort of principle for both of them. So they're both going to have 4 fractions in their partial fraction decomposition. Okay, and then I build up the s plus 2. So first I started with the first power, squared, and then cubed. Oops. And then my 4th factor is s plus 3. And every factor of the denominator, every irreducible factor is linear, so all of my numerators are just going to be constants. Okay, so then I would multiply both sides by the LCD. And the LCD is just the denominator on the left-hand side. So this right here, this is the LCD, right? So on the left-hand side, I'll just be left with the numerator. So I get 5s squared plus 6s plus 12. So what does the a need to be multiplied by? Well, only one of the factors of s plus 2 will cancel, so there will still be an s plus 2 squared and an s plus 3. The b cancels 2 of the factors of s plus 2, but there's still 1 left. The c, all of the s plus 2's are gone, but the s plus 3 is left. And then the d, the s plus 3 cancels, but all of the s plus 2's are there. So this particular problem, we're going to need to solve for 4 variables. So that means we need 4 equations. So we get to plug in 4 different values of s. 2 values should be obvious, and then the other 2 we'll just pick numbers that we think look nice. So s equals -2, s equals -3 are the nice ones. I'll do s equals -2 first. So 5 times 4 would be 20 minus 12 plus 12, so we just get 20. And then on the right-hand side, the a is gone, the b is gone, the d is gone, but c will be multiplied by 1. So just 20 equals c. Okay, and then I'll plug in s equals -3. So 5 times 9, so 45 minus, I'm just going to write this one, 45 minus 18 plus 12 equals, so if s is -3, the a is gone, the b is gone, the c is gone, and the d will be multiplied by -1 cubed, so that would be -d. So 45 minus 18 is 27 plus 12, so 39 is -d, so d is -39. Okay, well, we still have to solve for a and b. We're out of really nice numbers. So here's what I do is I think, okay, how can I make the stuff in parentheses equal either plus or minus 1? So if I plug in s equals -1, then s plus 2 is just equal to 1. So that's one that I'll pick. You can pick whatever numbers you want. You'll get 2 equations and 2 unknowns. You'll be able to solve for a and b. So let's see. So I'd have 5 minus 6, which is -1 plus 12. So I'd get 11 equals a times 1 squared, which is 1, and then -1 plus 3 is 2, plus b, -1 plus 2 is 1, -1 plus 3 is 2, plus c, -1 plus 3 is 2, and then plus d, -1 plus 2 is 1 cubed. I still get 1. Okay, so simplifying, a and b are my unknowns, so I have 2a plus 2b equals 11, and then I'm going to move the c and d terms over, but c is 20, so 2 times 20 is 40, but I'm subtracting it, plus d, well, d is -39, but I have to subtract it, so subtract -39, which would be plus 39. So -40 plus 39 is -1, 11 minus 1 is 10. and then I can divide the entire equation by 2. So I have a plus b equals 5. So there's one equation in a and b, and now I just have to plug in something else to get a second equation, and then I can solve the 2 equations and 2 unknowns. And I've already plugged in -2, which would make the s plus 3 equal to 1. So, and I've already plugged in -3, which would make the s plus 2 -1. So then I would plug in -4. You could also plug in 0, it's fine. But I'm going to plug in -4. So 5 times 16 is 80, minus 24 plus 12 equals a times, okay, so -4 plus 2 is -2 squared is 4. -4 plus 3 is -1. Plus b, -4 plus 2 is -2. -4 plus 3 is -1. Plus c times -1. Plus d times -4 plus 2 is -2, and I cube it, -8. Okay, so 80 plus 12 is, actually, let me do it this way. -24 plus 12 is -12 plus 80, so that would be 68. Okay, so I want to isolate the a and b. So I'd have -4a plus 2b equals 68. So here I'd have minus c, so I'd add it to both sides. So plus c, which is 20. And here I have minus 8d, so I would add 8d to both sides. And then d is -39, so 8 times -39. It might have been nicer to plug in 0. It is -312. I can see 2 goes into everything for sure. So -2a plus b equals, so -312 plus 88 is -224, but then remember I'm dividing everything by 2. And then here you could solve for b, right? b equals 5 minus a, and substitute it in right there. So I'd have -2a plus 5 minus a equals -112. So I get -3a, subtract 5 from both sides equals -117. Divide by -3, and I think you get 39. Yes, okay. And then b is 5 minus that, so b is -34. Okay, so now I have all of my numerators. So a over s plus 2. And then plus b, which was -34 over s plus 2 squared. And then plus c, which was 20 over s plus 2 cubed. And then it was plus d over s plus 3. And d was -39, right? Okay, and so going back to the time domain, f of t is just the inverse Laplace transform of f of s. And we can do it term by term. I'm going to put brackets here because I know I'm going to have the unit step function at the end. The 39 is a constant. You can pull out like in front of that fraction. And then 1 over s plus 2, its inverse Laplace transform is e to the negative 2t. And then minus 34. And then when you had it squared, remember, then you multiply by t. So I have t e to the negative 2t. Okay, what about when it's cubed? Okay, it's similar. I'm gonna put that 20 out in front right now, but we might need to kind of mess with that a little bit. So what about when it's cubed? When it was squared, we multiplied by t. If it's cubed, so think of if I'm using this formula right here with, so if it was s plus 2 cubed, then n is 2, right? Which means what we need in the numerator is 2 factorial, which is 2 times 1. So that means we need 2 in the numerator. And then when it goes back, then we'll have a t squared. So what I really want to do is save. So instead of thinking of that as 20, let's think of it as 10 times 2. And this is where I said, well, I might have to kind of mess with that 20 because I want the 2 in the numerator. So I'll leave the 2 there, but pull the 10 out in front. And then it was t squared, e to the negative 2t. And then the last one, minus 39, and then that's just e to the negative 3t. Okay, and so that would be the answer for this problem.